everybody. My name is Clayton Davis. I am the head of data science at Modzy, and today in this lightning talk, we're going to discuss detecting drift in MLOps. Now, as we start, the first thing I want to do is kind of level set on what I mean when I say the word drift. When I discuss drift, what I'm talking about is kind of this umbrella term that we use when we have models that have been trained well, but they're kind of misbehaving. There are three types of drift. There's prediction drift, where the class balances during production for outputs seem to change over time. There's data drift, where the data being provided to a model during production is different than the data that was provided to it during training time. And then there's concept drift, where the relationship that the models learn during training between inputs and outputs is no longer valid for some reason. Now, prediction drift and data drift are things that we can evaluate mathematically and we can kind of automatically track during production. So in this particular talk, we're going to focus on prediction drift and data drift. Concept drift is a little bit outside of the realm of what we can do automatically. So we'll come back at the end and we'll talk a little bit about what you can do to try to mitigate concept drift, but it's not going to be a part necessarily of our focus today. So for prediction drift, like I said a second ago, it's about evaluating a model and identifying when there's been a change in output distributions at different times during production. And so what we need to do is identify 2 times during production and then find a way to evaluate whether or not the data outputs in those 2 times are similar or dissimilar. And so the first thing that we do in prediction drift is we identify kind of a baseline interval. Now, this is a time during production where we believe that our model is functioning in accordance with what we would expect, and that the outputs of the model at that time are in line with our expectations. We take all of the data during that time, we push it through our model, and we get our class output predictions during that interval. This is going to be our baseline distribution, and it's what we're going to try to compare against data from a separate time. And so when we get our second time interval, this is usually the time interval that we're concerned about, or we think maybe the model isn't functioning quite the same way as we expect it to. We will again take all the data from that time interval, we'll push it through our model, and we'll create our second distribution. Now, in this example, you can obviously see that these 2 distributions are different, but eyesight is not sort of the metric that we're looking for. What we want to be able to do is tell when these 2 distributions are separate in some sort of mathematically significant way. And in order to do that, we need some sort of mathematical correspondence. And for prediction drift, that's a fairly simple one. We basically say that we're looking for times in which the probability of a particular outcome at time t0, which is our baseline interval, is just different than the probability of obtaining those same outputs at some other time, our second interval here during production, some other time later. There are a whole slew of mathematical approaches that you can take to try to tell whether or not these 2 distributions are different. At Modzy, we actually tend to use a chi-squareds test, where we'll take the 2 distributions, we'll compare them with a chi-squareds metric, and then we'll decide whether or not we need to do any alerting for our end users based upon feedback that they've given us during our drift setup process. But if you're setting up your own drift detection solution, you obviously don't have to sit around and just use chi-squareds. You could use things like Jen and Shannon metrics or earth mover distances, whatever your technical team happens to be most adept at and familiar with using. So that's prediction drift. You're basically looking at output distributions, and you're trying to tell if they are significantly different in some sort of meaningful mathematical way. Data drift, on the other hand, is not about the outputs of the model. It's about trying to identify when the data being fed to the model is different than the training data that was provided to the model in some sort of, again, meaningful way. And so again, what you're going to have is 2 different time intervals where you're going to be taking data and putting it through your model. But the differences here between prediction drift and data drift start at selecting those particular time intervals. Since data drift is always a comparison with your training data, you're always going to use your first interval to encompass the time of training. So you'll take all of the data that you used in order to train your model, you'll push it through that model, and you'll look at the way that that model behaves when the data is provided and pushed through it. Okay. And when I say behavior, I don't mean the inputs or the outputs like you would normally think of it. What I mean is that you want a sense of how the model is reacting and kind of the intermediate representations that exist for the data within the model. And so a well-trained model will start to group together data from particular classes at the intermediate layers that sit between input and output. And so what you're trying to do is get an understanding of what those representations look like. And so for a neural network, what you're going to do is you're going to kind of look at the middle of the network, and you're going to kind of see what did those intermediate representations for that network look like when, say, your model is trying to classify a car, and we'll say that's kind of in red, versus classify a motorcycle. In that case, we're kind of in blue here, right? Grouping of intermediate representations for models happens as the model gets better and better trained and more adept at performing its task. Importantly for you, that means that you have things that you can look at, in this case, the representations that you can look at to determine whether or not data being pushed through a model corresponds to similar data that the model has seen before. And so what we do is that after we take our training data, we push it through the model, and we build these intermediate representations, we take a second time interval during production. We take all the data from that time interval and we push it through the model, and then take the intermediate representations for the second time interval and look at them in relation to the representations from the first time interval. If data from production ends up in the same sort of locations for intermediate representations as the training data did, say, for example, this green star sitting here inside of this red cluster, then we can be relatively sure that the model has seen this kind of data before, right? However, if the data you take from production through your model ends up with some sort of intermediate representation that is far away from the clusters that are created from your training data, what that's telling you is that your model has never actually seen data like this, and you shouldn't necessarily be trusting the outputs of the model because the data itself has drifted away from the type of data that was used to train the model. And so that's data drift. Mathematically, what you're looking for are situations in which the probability of encountering a particular input is different in production than it was in training. And when I say different, I mean significantly different. Like there was a very low probability of encountering this data in training versus in production. And so that's the mechanism by which you would identify either prediction drift or data drift. And mathematically, you can use tools that are commonly available to statisticians to determine whether or not your model happens to be drifting. But a good solution isn't just about being able to take numbers and push them through an algorithm. There are three things that you need to make sure that any sort of drift solution you're looking at or trying to implement contains. The first thing you need to do is make sure that before you calculate any sort of value, that the data that sits inside of those time intervals we were talking about produces a distribution that's stable enough for a drift calculation. When you're looking inside of those time intervals and you're pushing all that data through the models, sometimes you may only have 30 or 40 examples. And while that may seem like a lot, if your classifier is trying to classify 1,000 different classes, then the distribution that you have is not necessarily a good one for calculating drift. At Modzy, what we do is we take a look at various entropic values and wait until we see that the distributions inside of our time intervals are stabilizing so that any sort of drift calculation that we're going to do can have some sort of reasonable expectation of providing information to an end user, that the drift metric itself is effectively useful. Okay? So that's the first thing you want to do, make sure that you've got enough data sampled in both of those sort of time intervals that the calculations you're performing are going to be actionable to end users. The second is that you want to provide end users or whoever's going to be observing drift the ability to tune logging parameters. Okay, some models are really important, and end users want to be notified anytime there's any sort of slight drift associated with that model. In that case, you want to log drift deviations pretty regularly, perhaps as much as every single time that drift is occurring. Other users, or for less important models where drift isn't as big a deal, only want to be notified in some way if the drift is significant. And so for them, you want to allow them to set lower thresholds so that they don't have to go through reams and reams of logs to find out whether or not their model's drift is actually important to them. Okay, so the second thing you want to do is be able to decide whether or not your logging is going to happen consistently all the time, or whether an end user just wants sporadic logging of their drift so that they can do their own evaluation and analysis later without having to look through a whole lot of false alarms. Now, the third thing is related to the second thing. The third thing is having a monitoring and alerting system available to your end users. All right. In step 2, you want to make sure that you're logging appropriately, but in step 3, you want to make sure that you're notifying the end user appropriately. Okay, so you basically need to do that in 2 steps. One is some sort of monitoring capability where you can see trends over time. If you're only having slight drift, that may not necessarily be a problem for an end user, but if that slight drift is incrementally happening over the course of months, and at the very end of your monitoring, you are significantly drifted than from the beginning of your monitoring, that's something that an end user needs to be able to see and needs to be able to take action on. So things like GUIs make a really good way for someone to be able to monitor drift over time. The other thing you need to be able to do is alert an end user, especially in those cases where drift is a big driver for the end user to take action. Something as simple as an email alert will help go ahead and suffice in those situations, so that the drift has not only been caught, but that the drift has now become actionable for your end users. And that's really it for this lightning talk on drift. We went over the 3 different types of drift: prediction drift, where your class imbalances sort of change and how you can identify that using standard statistical tools; data drift, where people are feeding data into your model that's separate from the type of data that was provided to the model during training, and how you can identify that by looking at kind of the body language or the intermediate representations of your model. And we touched a little bit about concept drift at the beginning. I told you we'd kind of come back to it here at the end. Concept drift can't be identified mathematically because concept drift is the product of the environment in which the model is operating changing. If you think about creditworthiness models that were built prior to the 2008 recession and housing collapse, those models were good up until 2008. And then after 2008, those models were no longer very useful. And the reason isn't necessarily because the model changed at all. It's because the idea of what constituted creditworthiness changed out there in the world. And so the relationship that the models have learned between inputs and outputs were different. The only thing you can really do about concept drift is go ahead and have a solid QA team in place to periodically sample inputs and outputs and make sure that as the world around the model evolves, that the model is still operating within acceptable parameters and the same sort of parameters that it was operating with right after it was trained. And that's it for today's talk on drift. If you have questions, you want to follow up with me, again, my name is Clayton Davis. I'm the head of data science at Modzy. You can reach out to me at modzy.com, our Modzy Discord channel, or on my LinkedIn or Twitter accounts. Thanks for your time.